In section 9.5, it's called Properties of Logarithms, and we do just that. We cover three objectives, 17, 18, and 19. Basically, we're going to do three things. We're going to evaluate logs by applying their properties in expanding and also by condensing. In addition, we're going to apply the properties of powers of logarithms to that. So we're just going to basically use all the properties you learned of logarithms last year. Let's look at the notes. Now I do want to show you this picture. This is John Napier, and he is the individual that discovered and created properties of logarithms. And this is kind of interesting to note here is logarithm functions are inverses of exponential functions. So what happens, because a logarithm is the inverse of an exponential, they have very similar properties. So when we look at the properties, just make the connection between this. You'll also notice how old this guy is. Logarithms were created, or discovered more so, many, many years ago. Again, the main reason for logarithms is to allow us to deal with very large and very small numbers, mainly in the science field. Now, the first theorem to look at for logarithms is this. Log base b of 1 is equal to 0. And this is very easy to see if you rewrite the logarithm as an exponent. Remember to rewrite a log as an exponent, start at the base of the log and just kind of swoosh around. So this would say b to the 0 power is equal to 1. Any exponent raised to the 0 is going to be equal to 1. Another property is this, log base b of b equals 1. It's easy to see this if you rewrite it as an exponent. B to the first power is b. This would say b to the power of 1 is equal to b. That makes sense. Therefore, when you have log base b of b, or it's the same number, the answer automatically equals 1. The other thing you want to take away from here is the power of the base. What you can do this. If you take a look at this, it says log base b of b to the n is equal to n. Well, again, I'm just going to rewrite it. B to this power is that. So b to this power is b to the n. It should make sense that the answer here is going to be n. Let me show you how to use these properties. This first example, evaluate log base 2 of 32. I'm going to just set it equal to x so I can rewrite it and do this. Base 2 to this power is that. So 2 to some power is 32. The answer to my problem is 5. So log base 2 of 32 is the same as saying the number 5. Now this slide here is going to address what we call as the expansion thing I talked about. I'm expanding logarithms. What you want to remember is this property. If you have the log of two variables in here, you can actually pull it apart through addition. So log base b of x times y is the same as saying log of x plus the log of y. On the other hand, if you have division, log base b of x divided by y can be pulled apart to look like this. Log of x minus log of y. Me highlight is very important that you notice it pulls apart into two different logs. It was one log and now it breaks into two. Same thing here. It was one log but it breaks itself into two. Where that comes from, by the way, is again Napier discovered logarithms through exponents. You see that in the world of exponents. When you have two base numbers that are being multiplied together, you add their exponents. Well, that's why this multiplication here becomes addition. On the same relationship, when you have division of exponents, they're the same base, so you can subtract their exponents. Well, because this right here is division, it actually becomes subtraction when you pull it apart. So if you forget, you can kind of just remember about exponents and hopefully make a good inference on how to pull these apart when you're doing expansion of logarithms. Let me show you how you're going to be challenged to use this in the book. And this is the type of problem you could expect to see on a test. Without a calculator, so basically show me enough work to prove to me you can do it without a calculator. What is the log of 6? Well, it's very easy to find the log of 6. You take your calculator. This has to be a base 10 number because it's not written. So it's really log base 10 if you want to look at it that way. So use the log button. Hit log of 6 and you're going to see that the answer has to be 0.778. Okay, fine, but it says without a calculator. So how could you do this without a calculator, given the fact that I am telling you log of 2 and log of 3? Well, you could do this. The log of 6, you can rewrite 6 as being 2 times 3. Okay? Now, the property of logarithms say if you have two numbers that are being multiplied inside the log, they can be pulled apart to be log of 2 plus the log of 3. The log of 2 is this number. The log of 3 is this number approximately. So plug those in. And when you add them together, you're going to get the approximate number the calculator gave. All right. I want you to pause the video for a second and think about how would you do the log of 20 given the same fact here. Go ahead and pause it and see if you can come up with it. Okay. What you can do is this. This one has actually a little bit of a twist to it. The log of 20, I have to use a 2 or a 3 or something else. Well, the only thing I can think of is that 20 can be written as 2 times 10. I can't get multiples of 20 using 2s and 3s, but I can use 2 and 10. Why that's important is because this is a log base 10 problem. So what I can do is pull this apart. I can do log base 10 of 2 plus log base 10 of 10. Okay? Log base 10 of 2 is the same as log of 2, so that is 0.301. But what is log base 10 of 10? Well, this is from the rules from before. If it helps you think about it this way, what is log base 10 of 10? Well, if we rewrite it as an exponent, 10 to what power is 10? The answer has to be 1. So log base 10 of 10, when you have the same base, is just the number 1. Add this together, you're going to get 1.301. And if you want to check, go to the calculator, hit log in 20, and you're going to get this exact same number on the calculator. These two are some good extra examples, so if you want more practice, I definitely would encourage you to pause the video, try A. I'll come back on and show you how to do it. Pause again and try B. If you're comfortable with it, just bypass this slide and move on to the next slide called Logarithms of Powers. So go ahead and pause the video, and I encourage you to try breaking down the log of 12 using the same two facts about the log of 2 and the log of 3 from the previous slide. Here's what the log of 12, how it can be broken down using the numbers 2 and 4, or 2 and 3. 12 is the same as 2 times 2 times 3, or 4 times 3. The 4 can be broken down into two 2's. So what you can do is expand this thing out. You can break it into log of 2 plus log of 2 plus log of 3, substitute in, and get this accordingly. Okay. If you understood that one and want to try B, go ahead and pause. Otherwise, fast forward ahead. So pause your video for log of 30. The answer for log of 30 is the only way I can break 30 down using 3 and 2 would really be 3 and 10. And again, use the 10 because this is log base 10. If this wasn't log base 10, then I wouldn't want to use the 10. But the special property comes into play. Log base 10 of 10 is just the number 1. That would be the same, you guys, if we had log base 6 of 6 or log base 7 of 7. It would be the number 1. And then the log of 3 they gave us. Thus, we have the answer of approximately 1.477. Now, this next slide is going to introduce a property about the exponents within powers. Log base b of 9, by the way, we can write it two ways. We could say log base b of 3 times 3, and we could pull that apart to be log base b, whatever that is, of 3, plus log base b of 3. Well, if you add those together, there's 2 log base b's of 3, so I'd say there's 2 times log base b of 3. Well, what that just shows us is we now have a trick that we can use. What we can do is, instead of expanding this out, we can make this connection. I could also write this as log base b of 3 squared. The trick here, in the world of logarithms, any exponent here can be pulled down in front and be written as 2 times log base b of 3. What we pretty much just did is a little proof showing us that they both mean the same thing. By far, it's going to be easier or quicker to pull down the exponent. So, for example, with log base b of 16. By the way, if I wanted to pull 16 apart, I could use 8 and 2 and do log of 8 plus log of 2. I could use 4 and 4, log of 4 plus log of 4. I can also notice this trick. Log base b, 4 is the same, or 16 is 4 squared. Fine. Whenever there's an exponent, it can always be brought down forward. So we're going to get 2 times log base b of 4. Okay. By the way, you can always take a number in front of it and pull it into an exponent if you want to go backwards. That's what this rule right here is telling you. Whenever you have an exponent in a logarithm, it can come down in front of the log, and conversely, you can go backwards with it. Let me show you how this is used to help you solve problems. Again, you're going to notice this chapter has had a lot of no calculator stuff. You might have a calculator at your disposal, but show the work that proves it. For example, here, the only thing we can use here is that the natural log of 17 is approximately 2.833. By the way, remember, natural log is the same thing as log base e of 17. This means the same thing, okay? E is just Euler's number. It's its own button on the calculator because it's found in nature. It's kind of like pi. All right. Use this without a calculator. It's pretty easy. This is an exponent. It comes forward. So this is the same as 10 times the natural log of 17. Well, the natural log of 17, they told us. When you times anything by 10, the exponent is just going to move over. This answer is 28.33. Okay. This next one, a natural log, the 4th root of 17. Well, I would rewrite it as this. The 4th root is the power 1/4. That exponent can now come forward. Okay. Take 1/4 of 2.833. You might get a calculator out for this. You're going to get approximately 0.708. Now the last concept we're going to cover in these notes is called condensing. So we're going to take expanded logarithms and crunch them together into one logarithm. So we're just going to go backwards from what we did before. Everything works backwards, so let's do that. Rewrite letter A as a single number. All right. So first thing you want to do when you look at the logarithm is realize this 2 can actually come up and become an exponent. So this is going to be log of 40 plus log of 5 squared. 5 squared, by the way, is 25, so I could do that. Now, these are the same base. They happen to be base 10. Again, we don't write the base 10, but if you want to put it there, you can. Because they're the same base, I can continue to crunch them together. So you would go backwards here. This would be the log of 40 times 25, and that together is the log of 1,000. Okay. Now, if you wanted to solve this, the log base 10 of 1,000 equals what? Again, if it helps you, put the base 10, and it equals what? You can rewrite this as an exponent quite easily. 10 to some power is 1,000. Well, what x has to be is 3. So this is actually the same answer as saying the number 3. Okay, let's take a look at another one. Letter B here has both addition and subtraction. So when we crunch it together, addition becomes multiplication, subtraction becomes division. So you can actually do addition first or the subtraction, it doesn't matter. I'm going to go ahead and actually bring together the addition part. So log base 2, I'm going to do 3/5 times 5/2. And I'm just going to leave this to the end a little bit. This will give me log base 2 of 3/2 minus log base 2 of 3. Now when I crunch it together, I'm going to bring these two logarithms together, so I'm down to 1 log. And it's just going to be 3/2. You can divide this by 3. 3 divided by 3 is going to be like multiplying by the reciprocal, so you can clean this up by doing this. So we end up getting, here is log base 2 of 1/2 is what it simplifies down to. Okay. Now if you wanted to solve this, this is actually pretty easy to solve again. What I would do personally is say it equals something and just rewrite the log as an exponent. So 2 to some power is 1/2. The answer here would have to be -1 to make it the exponent. So log base 2 of 1/2 is the same as saying the numerical integer number of -1. If you want more practice, pause the video and try this problem. If not, I would skip past this one and go to the next. Here we go. Pause the video and try it. This is the condensed logarithm that you should have gotten for this particular problem. And again, this is log base 10. When you condense it down, we're going to have this particular setup. So just be careful. Some things to highlight. Remember, when you multiply 3/5 to the 5th power, this 5 goes to both. So you're going to get this format here. Multiplying fractions, you just multiply straight across. And that would be sufficient for this problem. Now this one is worth looking at because it's in a natural logarithmic form. Remember, if it helps, natural log is the same as log base e. So let's go ahead and do this. Simplify into 1 again. So condense it down. I'm going to bring that exponent up. So this is natural log of t to the 1/3 plus the natural log of 5. This comes together as the natural log of 5 times t to the 1/3. And that actually is the simplification of the problem. Be careful, that 1/3 is not related to the 5 at all. It is only a cube root of the number, or the letter t in this case. Now this slide, we had already found that when we condensed this down, we got the natural log of 5 t to the 1/3. And what they're challenging you to do is just pick a number for t and see if this side actually does equal 1/3 the natural log of t plus the natural log of 5. Let's say you chose the number 2 for t. You're going to realize whatever this gives you in the calculator, you will get the same answer here. If you don't, then you're typing something in incorrectly. So if you have some time, go ahead, try t as 2. Put 2 into here, see what you get. Put 2 into here and make sure both sides equal. This is the last slide we're going to look at, and I'll tell you it's my favorite problem in this section. And let me show you here. We have two fellows, Stephen Boone and Curtis Cooper. Back in 1999, there was a company called Electronic Frontier Foundation, and they were offering a $100,000 prize for the person to find a prime number with more than 10 million digits in it. So those are the digits, okay? These fellows actually won that prize. Or did they, is the question. So here's the deal. This was the number that they came up with, was 2 to this huge power minus 1. They said was the largest known prime when it was discovered in 2006 by this team right here of these fellows. Did they win this 100,000 prize back in 1999 that this company put out there? So what we want to do is try to figure out what this number is. Now, if you put 2 to this 32 million power in your calculator, it's going to have an overload. It cannot do it. It is by far too large of a number. Remember, we're seeing if this thing has a 10 million digits to it. So let me show you how to evaluate this problem. It's actually pretty interesting. I think we can all make the same gesture that this number here is going to be huge. And if you subtract 1 from a really huge number, it's not going to make much of a difference. So I'm going to ignore the fact of the minus 1 and just do that. And with that, we're just going to write 2 to the 32,582,657th power is equal to x. Now, here's why logarithms were created, because I can't visualize this number even with a calculator. I would need a supercomputer. So what I'm going to do is a trick here. I'm going to take the log of both sides. It's an equation. As long as I keep it balanced, I can do that. I did the log to one side, I can do the log to the other. Because I've done that, I just gave myself the ability to take this exponent and move it down. So this is really the number 32 million here. Times log of 2. And that equals the log of x. Now I can actually get the calculator out this time and I can punch in log of 2 and times it by this number. And when I do that, it's going to be a pretty big number, but here's what it is. It's going to be 9,808,357.0954,316 is equal to the log of x. Now, this is just a simple logarithm, and when you look at it says log of x, it's actually log base 10, because that's the number counting system that we use. So what I want to do is I can take this log, base 10 of x, and rewrite it as an exponent this time. Because here was the problem. When this number they came up with is base 2. Base 2 is a different counting system. We use base 10 counting, so we can understand base 10. So whenever you have an exponential number that's not a base 10, but in this case a base 2, it's easier to rewrite it as base 10. So let me show you. If we rewrite this, we're going to have 10 to this power equals x. So I will write that right here. So it's going to be 10 to the 9, 808. Is equal to x. Okay, now here's where the property of exponents come into play. I think we all can agree that this number here plus this little decimal would give me the entire exponent. So what I'm going to do is pull apart this integer number plus this decimal number. So what I can say is this. X therefore has to be equal to 10 to this 9, 808. 357 times 10 to that decimal. Okay. What I've just done is rewrote this so I can actually understand it. I can take this number as it stands. I can put 10 to the 0.09543 decimal in my calculator. When you do that, we're going to get this. You're going to get 1.24575, again, times this 10 to this very big power. Now, this number in front of us is rewritten in scientific notation. This is about 1.2 times 10 with all of these zeros. Did these guys find the largest prime number it had over 10 million digits? They did not. They were very close. Their prime number had 9,808,357 digits in it. And that's how you figure out this problem. Definitely a higher level math problem, but worth seeing. For the homework, I have 2 adjustments to it. You can just do 13a instead of all of 13, and then go ahead and skip number 20. Good luck on the homework.